In this work, we consider the challenging task of 3D human key point estimation from in-the-wild point clouds. Training a 3D key point detector in a supervised manner requires large volumes of high-quality labels, which is expensive to obtain. For this reason, previous research has mainly focused on utilizing different kinds of weak supervision. However, prior works have largely overlooked the valuable information present in the large amounts of unlabeled sensor data. We present GCKPL, a method for learning 3D key points for in-the-wild point clouds without any manual key point annotations. We effectively utilize large amounts of unlabeled data by using a set of unsupervised losses. Our method achieves reasonable performance as compared to the fully supervised approach. Further, the backbone benefits from the unsupervised training and is useful in downstream future learning. The idea is simple. We take a state-of-the-art backbone model pre-trained on synthetic data to predict key points and parse segmentation on real data. Then we train it using a set of novel unsupervised losses, which constrain the output space by using geometric and kinematic constraints. The complete training pipeline of GCKPL consists of two stages. In the first stage, we initialize the model parameters on a synthetic dataset. The purpose of stage 1 is to warm up the model with reasonable semantics. The second stage generalizes the model to real-world data. In this stage, we use our unsupervised losses to refine the key point predictions on in-the-wild point clouds. Next, let's delve into more details. The goal of stage 1 is to warm up the model to a reasonable state to start the main optimization. During this stage, we use an L2 regression loss for key point locations and cross-entropy loss for point semantic segmentation. Unsupervised training with real data is hard, so we start from using synthetic data and later, when all parts of the model prove to be working, switch to learning with real data. We construct a synthetic dataset with sequences of randomly posed simple body models. For each pose, we extract 3D joint coordinates, lidar points by ray tracing, and parse segmentation labels for each lidar point. We use ground truth labels for synthetic data because they're readily available. Alternatively, we could also apply k-means clustering on the lidar points and get surrogate ground truth labels from clusters. The method works in both configurations, but if ground truth for synthetic data is available, overall results are slightly better. We find that data augmentation is essential in stage 1 training. To simulate real-world noisy background and occlusion, we apply various data augmentations to the synthetic data, including random downsample, mask, etc. In stage 2, we further refine the network using unsupervised learning. The network is the same, but data and losses are different. For stage 2, we use only real data without any labels. We use a novel set of unsupervised losses for learning the key point locations. We designed unsupervised losses based on the key insight that humans are comprised of approximately rigid body parts, and human skeletons are generally centered within rigid body parts. The position and motion of surface points should be able to explain the movement of the skeleton and vice versa. With this in mind, we devised novel unsupervised loss terms to train our model in determining the locations of 3D key points within human point clouds. All three proposed losses are defined in terms of surface points in each predicted limb's local cylindrical coordinate system. Therefore, we first convert all input lidar points to each limb's local coordinate system and compute radial and axial coordinates. First, we assume that points on the limb move with the limb and should stay roughly at the same location in each limb's local coordinate system. To account for this, we propose flow loss. Flow loss considers the predictions from 2 consecutive frames and encourages consistency of the radial and axial components of all points with respect to scene flow. In other words, limbs should move between frames in a way to keep radial and axial coordinates for all points constant. Second, we use points to limb loss, which ensures that all lidar points are close to the predicted corresponding limbs. taking into account that lidar points cover only one side of the body, which is closer to the vehicle. So if it is used alone, this loss will force the model simply snap a line segment somewhere near the visible surface of the body part. Therefore, we propose another loss to counteract, symmetry loss. It encourages the predicted limb to be in a position such that all points around this limb are roughly symmetrical around it. That is to say, points with similar axial coordinates should have similar radial values. To compute this loss, we need to estimate the densities for radial coordinates conditioned on their axial coordinates. We use kernel density estimators with Gaussian kernels to do this. Having this conditional density, we compute expected radial coordinate for lidar points with the same axial coordinates. The symmetry loss then measures how far away each lidar point is from its expected location. It ensures that points with similar z values have low variance of the radial distance, or in other words, points should roughly lie on a rotation surface. This visualization demonstrates the effect of the proposed unsupervised losses. Here, we perturb the ground truth key points by adding a random noise to each key point. Then we minimize these losses with respect to the key points. As you can see here, the losses effectively move the perturbed skeleton to locations that are closer to ground truths. Here, we visualize the predicted key point on one example point cloud at the end of stage 1 and stage 2. As shown, after first stage, we're able to predict reasonable human key points. The second stage further refines the location of the predicted key points. We conducted few-shot experiments where we fine-tuned with a small amount of data from Waymo Open Dataset to represent challenging scenarios where only a limited amount of annotated data is available. Results suggest that our backbone learns useful information from the unlabeled in-the-wild data and enables a significant performance boost on the downstream tasks. The improvement remains consistent across all data regimes, demonstrating robustness and effectiveness of our approach. We show qualitative results from the downstream experiments. As shown, models fine-tuned from our backbone are able to capture fine details on the arms and overall produces more accurate results than state-of-the-art. Thank you for listening. Please check out our paper for more details.